will also say very welcome today to this talk. And yeah, before we start, some few words about me, but this will be like very short because a lot of you know me already. So yeah, working as software engineer, talking Java and Kotlin. So this is the things I do most. I like giving workshops and talks like this one today, and occasionally I also do wakeboarding. So this is most of the cases the time when I'm not in front of my computer. So before we dive into this topic a bit more, at first the question, who of you actually thinks they do concurrent programming? So that is not a lot, but at least a few. So I guess at first we just need to think about what concurrency actually is. And I know this is a shocking question, but we will get here into the details anyway. So what is concurrency? So Rob Pike once said, concurrency is actually like dealing with a lot of things at once. And this gave me the idea that concurrency is more about the structure of the code. So how the code is organized, and in order to code to be concurrent, it must allow for out of order or partial order execution. And what does it mean? That means in fact that executing the execution order of your code should not affect the outcome. Yeah, so your concurrent code that runs concurrently should be able to be reordered in any way, and the outcome must not be affected by this fact. And of course, concurrent program parts should be able to run independently. And if you meet all these requirements of concurrent code, and then in the end your code will allow parallel execution. And this again made me think, okay, if it allows for parallel execution, then maybe concurrency is not the same as parallelism. So let's come back to the quote from Rob Pike. He said, concurrency is dealing with a lot of things at once, and parallelism, he said, is actually doing a lot of things at once. So we have two different things here. So today it's more about concurrency, and now that we know a bit more what concurrency means, we could ask ourselves, so why should we even think about concurrency? Like most of you didn't even think they do concurrent programming, so why even bother? But in today's world, in the modern software systems, we often use concurrency. And as a matter of fact, we also use then a lot of parallelism, and we will see in a minute why this is the case. Just think about maybe horizontally scaled microservices. Even though if you are writing your code, it doesn't really seem like you're doing concurrent programming. Yeah? But if you have microservices and you have two instances running, and there are two requests that are handled by each of these instances, then these executions will happen concurrently. And it's the same with the web server itself. So under the hood, the web server hopefully uses threads and allows you to execute multiple different requests for the web server concurrently. And hopefully Moritz does not need to wait for its web request to be executed before mine has finished. So this would be a really boring world where we all have to wait for all the others to finish their web searches. And also a thing that is, I guess, very modern today is message processing. And also in message processing, if you think of maybe Kafka and having different partitions and a lot of consumers for all your message streams, they hopefully do their work concurrently and in most cases even in parallel. So even though while just writing your computer programs you don't really recognize it, most of your code will be executed concurrently. So how is concurrency then handled in Java? Because that's actually the topic we're here for, isn't it? From my point of view, there are like two different levels of concurrency, and we spoke about one of these levels beforehand when I showed you the examples, the real world examples of concurrent code. And the first one is then just like having multiple JVMs. So the program runs or your different program parts run in multiple JVM or even the same program part, and you can obviously execute these concurrently. And the other level is like using Java threads, and this is when you are in one JVM and you want to do concurrent stuff, then you basically need to use them. And this is the thing we're going to talk a bit like in depth now. And but before we go a bit deeper, at first the question, when is concurrency hard? Does anyone maybe have an idea what makes concurrency hard? I mean, there's a hint in the title, so maybe somebody knows. Lukas?
When threads use shared data.
Yes. Of course, it gets hard when we have shared resources. Yeah, so if two parts of the program need to access the same resource, then the trouble starts. Of course, a little side note here, there are also other things about concurrency that are not easy. And here I recommend you this talk from Rob Pike that you can have a look at. And one of the problems that is not easy is like decomposing a problem into concurrent parts or into other parts that can then be executed concurrently. And this talk, the slides are online under this link, is really explains it in a really good way, why it is a problem and where it gets hard. And even though it's in the Go environment, I think everything Rob Pike says here in this talk also holds true for most of the other programming language. So this is a really good read. So, but back to concurrency and why is it hard and when is it hard, and Java. So how does concurrency work in Java? When we we'll do some research on this, then we'll maybe see like this image, and we see, okay, we have here the main memory and threads, and there's a lot about memory model we need to think about and how instructions are ordered. And there's this image here is from the JVM specification version 6. There's a lot of more description on how this works there. I really tried to find like the same images and things in the latest specification, but in the latest JVM specification there's no talks about threads, but luckily in the Java language specification there's a lot about a lot of things you can read about there, how it really works, so when threads read which variables and kind of stuff. But from my point of view, I think it's like very scientific and very hard to swallow, and for this talk I wanted it to be like a little bit more fun. So I came up with these two guys here. So we have our little painter guys, and these two guys, they have a task, they should paint the wall. And each of these guys should paint one half of the wall that is not yet painted. So now let's assume these two painters, these two happy guys, they are threads, and the wall is our shared resource. So now the question, what can possibly go wrong? And so for this we need to think a bit like the JVM would think, and at some point each of these threads would load the shared resource from the main memory. So every thread has their own part of the memory, and they need to load the shared resource from the memory. So now we have this image. So what could happen now? Anyone an idea? What?
Each of them paints a bit of the wall. They paint the same bit, try to store it, one overwrites the other.
Yeah, that's basically what happens. So we could have like this, and then the threads will write the state of this resource back into the heap, into the main memory, and then the wall looks like this. But it mustn't. It could also be the case that it looks like this, because if each of the threads decides to paint the other half of the wall, then it would like this. It would look like this, and it could also look like this. And but in the end, one might think, okay, in the end the wall is red, so we're good to go. No real problem here, isn't there? So let's make things a bit more interesting. So if we look at this, one guy has red and one guy has blue color, then again they need to load the shared resource. So now they start to paint, and what is the result now? Christoph?
Red or blue, depending who writes last.
Yeah, it could be this or this.
Or?
Yeah, there are a few other states that could also happen, but this is the most interesting one. So we will concentrate on this now. So what is the problem with this behavior?
Missing synchronization.
Yeah, that is the problem, and
Non-deterministic.
yeah, correct. So the behavior is not deterministic. So in the end, we don't really know what happens, and if we write computer programs, we possibly want to know what happens. Yeah. So and I don't know if you ever had such kind of a problem, but if you have this kind of race conditions, then good luck debugging this. Yeah, so the problem here is the race condition, and how can we solve this? And now Moritz is completely right. We can obviously solve this with synchronizing the access to the shared resource. So, and synchronize just means if we go back to our painter guys, and we assume they are not threads but people, then they would obviously talk to each other and say, you pay this wall, I pay this part of the wall, and then we go on. Yeah. So how can synchronization be done in Java then? And maybe the image indicates something here, but I guess someone already knows. So in Java, we can use mutexes, and this means mutual exclusive access. What does it mean in the end? It just means that only one thread, so only one part of the program at a time, can access a specific part of the code, the so-called critical section. And in Java we have for this the synchronize keyword, but we also have locks, and specifically we have reentrant locks and reentrant read-write locks. And we will have a look at how these things work in a minute, and when to use which. One thing that I can say right now is that you should avoid using synchronize, because locks are way more performant. because synchronized has some problems when there's a lot of thing or there's a lot of variables and instances that needs to be synchronized. It's a bit harder. So logs are typically the way to go. And one last thing are volatile variables. And what are volatile variables good for? They give you like atomic access to shared resources. That means the Java compiler will order the instructions in a way that if there is a write, then all subsequent reads will see the result of the write. So the JVM will then just reorder the instructions in a way that you can be sure. But volatile variables also have some problems that can occur according to the Java memory model. As I said, it's a bit complicated because there is like a rule set of when the code is like correct according to the Java memory models and to the order of the instructions, and that does not necessarily mean that the result of the code is correct. So you have to be also a bit careful with this. So one more word maybe about the synchronize keyword in Java. So in Java, or the Java JVM uses monitors for synchronization, and again, monitors, there's again a very scientific description that you can read on Wikipedia, but in the end these monitors are more or less like intrinsic logs. So every object, even class objects, they have such an intrinsic log. And intrinsic, of course, means that you do not really see this thing, that you don't really know about it, and the idea is that you also don't need really to care about it. But we will see in a bit that this can be dangerous as well, because you can likely produce deadlocks using these intrinsic logs. In the end, every time you access a synchronized block or a synchronized method, this intrinsic log is locked, and no other thread can access this part of the code. And only one thread at a time can have a lock on the monitor. And if you yourself try to write some concurrent code and use synchronize and maybe wait and notify in Java, then maybe you sometimes also had an error message like the object does not hold the lock, or the thread does not hold the lock on this object monitor, or something like this. A bit cryptic, but if you think about it in this way, then I guess it will get pretty clear. So now let us look at an example on how we can do these things. And before we need to click away these errors. I hope everyone can see quite enough, but I can also, oh no, this is not the right one, sorry. Need to go here, this is better. And I think maybe I will enter presentation mode. Is this big enough? So what I prepared here as an example is not our two little painters, that would be nice too, but I went forward here with the library. So we have a library, and the library, of course, wait a sec. What a library can, of course, have some books. And you can get a book, and you can rent a book, and you can return a book, but returning a book, we obviously don't need it here for this test case. And we can wait for the library to open. Now we already see here this synchronized and this wait, and we will see later why this may be a problem. And the library can also open, and in this case we will have this notify all call, and this will tell all threads like waiting here at this point to that they can go on executing. So, but that's only the library class. Then we have also a customer, of course, and a customer is just a generic customer that can like perform some task. Then we have we also have an executor. This executor can like use these customers to like let them execute their task using threads. In this case, I create threads using this thread new keyword and starting them here manually. This is not the best way you should do it today. Today you will most likely or should prefer to use executor services, but for the case of this demo here, this is good enough. So, and then we have a test case here, and there we can test shared resources. Yeah, what we do here is we have at first the library instance. We have one book, the Lord of the Rings, Fellowship of the Ring, and we have two customers that have here this task, rent book, and this rent book task just says here, get the book from the library and then rent it. And what will happen now in this test, that we can see at first here for demonstration purposes, it sometimes will run and sometimes it won't. Yeah, so now you see, at first we got 100% of the tests green, and now it failed with the first test, and you can already see the problem. It's the same with the with the wall that was painted. Now both threads or both customers, they were able to rent the same book, and this should not happen. Yeah. So how can we fix this? And as I said, there are two ways. We will at first have a short look at the synchronized scenario. Thank you, no internet. And in the synchronized scenario, we also have here this test. But what we have now, so this is the same test. We have two customers and they both want to rent a book. But now in this scenario, the code looks a bit different. So what we have here is that we have now here this synchronized block. Yeah? So we synchronize on a specific object here, in this case the book object, and then we rent it. And now we can just execute this test again, and it should be 100. We can also try it a bit more often to make sure, okay, this is really cool, this helps us. Yeah, so this looks good. So now we managed to get the right state. So in this case, I put it here in this rent book method, so to have it a bit more close to the test case and can have a look right away. Maybe a better location for this synchronized block would be here in this method, where the renting actually happens. So maybe the scope of the synchronize is a bit big. And there's maybe one thing you should really keep in your mind when thinking about synchronizing or locking. Locking means all the other threads, of course, cannot enter this part of the code. So the scope of your blocking part, so the scope of the critical section should be as narrow as possible. So that the part where things can be blocked are small, and so we have small blocking times. So, but we have another scenario. This was the synchronized. This was the synchronized block, but we could also use a synchronized method. And we have this synchronized method here, so the synchronized keyword is now here. And here we have like this code. At first we await the opening of the library. We can have a look at the test. In the test it says when the threads are all started, then we open the library, so all the waiting customers can finally go rent their book. So what happens now if I execute this test? Who might have an idea what can go wrong? So let us just execute it. So I will make this a bit bigger. So what happens now is that only one customer gets to rent a book, and then our code hangs. Yoo-hoo, hooray, we finally produced our first deadlock. So, and how did this happen? If we have a look at the code, then we see in this task here that we have here this library await opening. Yeah? And in this library await opening, we have a wait method. That means every thread that goes here needs to wait, and does nothing. But this whole method here is synchronized, so only one thread at a time can enter this await opening method wait. Because the other thread, as we see here again, in this test, we have like two customers, and one of these now can really access this method and waits for the library to open. Then the library opens, and this one thread that has the object monitor of this synchronized method at this moment will rent the book, and then the second thread will enter this synchronized method, and it will also execute this await opening code here. And this will then be stuck here waiting forever because the library is already open. Of course, there are some fixes that we can do here to fix this. So one thing is, I will not show it here because of the time, but one thing could be in this task here. No, this was not the correct method. Sorry. But one thing could be like to lift this await opening method or method call out of the synchronized method. Yeah, this could be one thing. Another thing could be using a state here. So when the library is open, maybe don't enter this wait block here. Yeah. And one good thing you should do, you should never do it like this here with this wait without any parameter, but you should always use a timeout here to not let your threads wait forever. So this is on the synchronized part of Java, and as I said before, it's not really recommended to use these nowadays. We will come to this a bit later as well, but we will have another method of doing synchronization in Java, and this is using locks. And these are a bit more interesting. Okay. It has been restored. Okay. So let's look at this test again. Oops. Let's close this to see a bit more here. So again, it's the same scenarios. Now in the rent book thing, what we do here, we now see that we have here a book lock. And this book lock is just an instance of reentrant lock. And we can like a bit use it like the synchronized block. Yeah, so if we do a lock here, then it will behave almost the same. So no other thread can now obtain this lock here. But what we need to really make sure in the end is also to unlock this lock again. Okay, this is the other example, but it doesn't matter. Like here. So we need to unlock this one. And one thing that I really recommend to you is that you use for this finally block. Because this is just a normal statement here, and if you put it here, and the library rand method throws an exception, then you are again in a deadlock state, because no one will ever unlock this book lock, and then you're doomed. So in this case, the rand method is relatively safe, but in other scenarios, this could be really a problem. So you should really use this try finally thing here. And we can again like just test it. So the rewrite, the reentrant lock should work like pretty much the same. We can also execute it like multiple times, and it should never fail. But one more interesting thing is the read-write lock. Yeah? And the read-write lock has one nice attribute, and it is that all read locks are non-blocking as long as there is no write lock. So if you have like applications where you have a lot of read access to a shared resource and only a few write accesses, then this can really help you out and will like make your reads really fast and only like a few waits when there's a write that is happening concurrently. And how does it work? So at first we have here like two different tasks. The first is like check book is available, and this check book is available is just a read operation. So I decided just to use the read lock here of the Java read-write lock. You access it like this, and then it's just the same as before with the normal reentrant lock. You just log it, and then in the finally block unlock it. And if you then run this test, it should like tell us all the time that the books are available. Oops, and it does so. So for all threads, the books are available. But if I now add another task here, bumps, like this one, where I will rent a book using the write lock. It's like getting the write lock from the read-write lock and then locking it and unlocking it. So we saw this, and it's almost the same as with all the other locks. But now when we execute it, then this test should not like complete like all of the time, because like in this case, at first the book was rented and then it was never available, and we can like execute it a couple of times. Like in this case, here the thread 5 and 4 were faster. They saw the book was available, then it was rented. But in the next case, again, the other thread was faster. And as you can see, it's a bit hard to see here in this example, but you can be sure that if a write lock is locked, then no read locks can occur, but if no write lock is locked, then the reads will like happen concurrently without any problem. Of course you can. So this is it about the example. Now we have seen how we can, like in Java itself, synchronize access to these shared resources. And I think even though nowadays we have a lot of frameworks that take really a lot away from us, in case of or in terms of concurrent access, so we don't really realize how it works. It's good to know how these things work in the background, and all the concurrency frameworks or all other frameworks that you use will basically use these techniques in their low-level code. And if you have somewhere problems with locks or race conditions, then you know what to look for. So now we finally one word on virtual threads. So virtual threads now are the new cool thing since Java 21, and they're really cool. And I already talked about virtual threads here a bit. So, but virtual threads are you get the most out of them if you have some blocking I/O operations somewhere, because under the hood, these virtual threads use normal Java threads as carrier threads, and these threads then execute their code on basically on normal platform threads. And if you have only if you don't have any blocking calls like writing to a file, writing or reading from a database, like some external resource you need to access, then the task of the virtual threads will just run in one go and will consume the same amount of CPU and thread time it would without using virtual threads. And when you have I/O operations or blocking operations, then the virtual threads will be parked, and the carrier thread, the Java thread that runs under the hood, gets free and can execute another virtual thread task. But what could happen is thread pinning. And what does it mean? Thread pinning means that the virtual threads will not release the carrier thread. So no other virtual thread can actually use it, because the virtual thread, so to say, reserves this Java thread. And this happens if you use the synchronized keyword. So if you use synchronized keyword or synchronized methods with virtual threads, then you should really make sure that the scope of this method is really, really narrow. So there's only a short part of the code that is executed in this block, and you should, in best, just avoid the use of this thing, because it will make the whole sense of virtual threads obsolete. And if you're using virtual threads, then you should just stick to locks. I read in somewhere that they are thinking about a solution on how to deal with this synchronized problem, but as far as I know, this is still there, so you should be really careful on this. And now that we've talked really a long while about the JVM and the threads and what happens in there. Some few things about distributed systems. So how do you manage concurrent access in distributed systems? Typically, or there are some things you can do. One thing is you can synchronize over the database or the file system. So I don't know if you use Terraform, every one of you, but Terraform, for example, uses log files to synchronize access to the Terraform state, for example. There are other frameworks or other systems that maybe use a locking table on the database. And if we are on a database level, we can think about optimistic versus pessimistic locking. Does anybody know what pessimistic locking is?
Basically, so optimistic locking is, or one of them is, if I might use the resource, I'm just going to lock it. The other one is basically only if I actually need to lock it, I'm going to lock it. And don't lock it straight ahead or isn't it?
It's almost. So pessimistic lock is like really a mutable exclusive access. So in that case, you're right. If you need it, you just really lock it. So pessimistic locking is this. And optimistic locking is that you, in fact, do not really lock at all, but you use like a thing of a hash or a version or something like this to make sure nobody else in the meantime updated your resource. So in databases, this is typically done with a version column. So you load the resource from the database. It has version 1, and every write to this resource will just increase the version. And if you then write back to the database with changed data, you check beforehand if the version has changed in the meantime. And if the version changed, then you're not able to write the data back. Yeah? So that is, of course, in the database, there will happen some locking if you do write operations and use transactions. You cannot avoid it. But optimistic locking from like the client perspective is like no locking at all. Yeah. And one thing you could also think about is Spring integration distributed locking. So Spring framework, I think everybody knows what this is. And the Spring framework has also a Spring integration part, and this is implementing enterprise integration patterns for Spring. This is like a really nice thing to do sometimes, and what it also offers is distributed locking. And how does it do it? It uses again a shared database and abstracts this locking in the database away, so that you in your Java code can just use Java locking semantics. So you have a lock implementation there that you can just use like we saw it before with this reentrant locks, just like lock and unlock, and the rest is abstracted away by the framework. One thing I forgot, we will just go back a bit. Maybe you wondered here about this reentrant thing. Does anybody know what reentrant means? Or did you just accept that this word is there? Christoph?
The thread that acquired the lock, basically that locked the thing, can go through the lock again. So it doesn't block itself.
Yes,
so
correct.
It can re-enter.
Yeah, that's the correct explanation. So reentrant just means the same thread can acquire the lock of the same object every time without blocking itself. And one thing maybe good to know is that it's synchronized. So the intrinsic lock of the Java object is also reentrant. Yeah? So you don't need to worry about this with synchronized. And now back to Spring integration again. So Spring integration distributed locking, these locks are also reentrant. So it gives you also like a bit of tooling to have like logs for different contexts and such things. It's a thing you can think about. And also, I don't have it here on the slides, but one thing you could also do to synchronize access to a shared resource is using a message queue. Yeah, so if you have multiple services that want to write to one shared resource, you could just put them in one single message queue in some arbitrary order or a random order or whatever, however you would like to do it. And then you have like a single threaded system at the end that will simply write one entry at a time, and you're good to go as well. So, yeah, and one thing that I think is, I don't know whoever had to deal with optimistic locking exceptions in their code, but if you use like normal Java locking semantics, you don't need to deal with them. And at least for automated system, it's quite handy because you don't. If you have like a web application and a client where a human is in front, you could just like throw it at him and he should like retry or whatever. But if you have automated systems, then what to do with optimistic locking, and maybe this can help you. So this is it for now, and I hope you enjoyed, and if you have any questions, just ask.
Any questions? Yeah.
Is there any test hardness, because this concurrent scenario is pretty hard to test? For example, you return your own test harness to create so many threads. So is there any tool that makes this concurrent?
I know there is a tool that is called Awaitility. I don't know if you ever have heard about it. I use this occasionally, but I also ended up sometimes like writing my own threads and notify await, like to produce the exact situation that maybe caused an error, but you don't need to do it very often. And most of the times, Moritz needs to do it very often, but
Logistics.
yeah.
Picnic logistics internally, everything message based. They had a shit ton of race conditions just because the system forced them basically to happen.
Yeah. So I would I'm also at the actual project I use Awaitility for this, and this is pretty cool.
Any new concurrent paradigms in, let's say, the latest one? Because what we discussed here is what has been there.
Yeah.
Classical concurrency. So is there anything?
So there will be structured concurrency, but it is only in preview right now. So I would rather not try, or you can of course try it, but I would not use it in productive code. So and I think structured concurrency is there in Kotlin now for quite a while, and I think it's quite popular there, and it makes code a bit more readable and lets you like handle these concurrent things a bit more in a structured way. It's in the name.
Okay. Okay, thank you.
Any other questions?